Okay, welcome back. In the last time, we have discussed the RS configuration nomenclature system for alene and biphenyl type of molecules, which are actually chiral molecules, and also the EZ nomenclature for double bond, and then the concept of pseudo asymmetry. Let us go back and again re-inspect the question of relative configuration. There are different nomenclature system. Yesterday, I was telling about trio-erythro system and then like and unlike system. Okay. Now, this actually created this relative configuration has created lot of confusion in the literature, as you will see as I describe in the next half an hour, that where was the confusion. First of all, this molecule is what is known as an erythro molecule, okay. Because what is the it originated from the carbohydrate erythros. In erythros, what happens? The OHs are on the same side. By the way, this is the classical D erythros. Similarly, there will be an L erythros where the two OHs will be on the left side. Okay. However, an erythro compound of this type, where two similar groups are present on the asymmetric carbon, the other groups may be same, may not be same. So, this nomenclature system is applicable for a system where there are two similar groups, at least you need two similar heteroatoms on these two stereogenic centers. Okay. The other groups may be different. Okay. And then this is erythro, but you can have another erythro compound where the two X's are on the left side. Okay. This is the another erythro. In many of the reactions, when we do the reactions in organic chemistry lab, we generate stereogenic centers while we do the reaction, and sometimes many stereogenic centers are created. And in many cases, absolute configuration is difficult to determine, because you need X-ray crystallography, but the relative configuration you can determine by NMR spectroscopy and other spectroscopic means. So, most of the time we will end up with describing what we got in terms of erythro or trio. Okay. That is why relative configuration is so important concept in stereochemistry, because most of the time we determine the relative configuration and not the absolute configuration. But nowadays X-ray crystallography has become much more has more power now. Crystal solving has becoming more easy, more routine. So, absolute configuration can be determined for molecules, but in many cases in organic reactions we have to describe the stereochemistry of the reactions in terms of relative configuration. That is why I am spending more time on this. Now, this is the erythro, this is also erythro. Okay. So, if I am asked to write the erythro molecule of this formula, then I have to write two molecules. Okay. And what is the trio? You know what is the trio? Trio is when the two X's are on the opposite side. Okay. And because it is a Fisher projection formula, actually it is not wise to show the customary is that you do not show the carbons. Okay. So, the carbons are not shown on the axis. These two, the stereogenic center carbons are not shown. So, these are the two erythro forms. Okay. Now, you have also been introduced to the other different projection formula. Okay. What are the other different projection formula? One is Newman projection formula. Now, if you convert this into the Newman projection, what happens? Better, see, for as you are a beginner, so better you do the wedge formula, convert it into the wedge formula first. So, this is X, this is X, and this is B, and this is B. Sorry, this is A, and this is the alpha carbon, and this is the alpha carbon. Okay. That is the wedge formula. You also number it. Suppose this is your number 1 carbon, this is 2, this is 3, and this is 4. Now, how do you convert it into the Newman? You look along the C2 C3 axis, or C3 C2, vice versa. Either you look from this side or from this side. Now, if you look from this side, that is little bit easier to visualize, because the molecules are usually held at the top of the board. So, it is easy to look from the back side. If you look from the back side, the way to write the Newman projection formula of this is that, first of all, you know that the front carbon is shown by a dot and the back carbon is by this circle, as if the front carbon is blanking the back carbon, and the substituents are shown in 3 lines, okay, 120 degree angle with each other. So, when you look at this from this side, this carbon definitely you can visualize and realize that this carbon is at the back, and this X will now be on this side and this B on this side. Okay. And what will be the C1 carbon? So, C1 carbon is also is in the same side of this C4. So, this is the C4 carbon. So, C1 carbon is actually eclipsed by the C4 carbon, and the X at C3, this is the C3 carbon, this is the 2 carbon, the back carbon, and this is the number 1 carbon. So, the other X is here, and this is the now the A. So, this is the correct Newman projection formula of this fissure, starting from this fissure erythro molecule. Okay. Now, the problem is that this is a molecule where all the bonds are eclipsed in the eclipsed form. Today, later on we will do the conformation of a cyclic system. When we will discuss, we will see what is the stability of this. Obviously, it is not very stable, because there will be repulsion between the steric repulsion between these groups which are eclipsing each other, and also there is what is called bond opposition strain, because the bonds are made up of electrons. So, they repel each other. So, this will be actually this will have the highest energy. So, in order to so there is a criticism of Fischer projection formula that the molecule actually does not exist in this form, because that is the form which is the fully eclipsed form as we see here. So, you better you have to convert it into the form which is the more stable form, and that is why what happens that there is another rule that came which says that write the molecule in a zigzag fashion, where the carbon carbon bonds, these carbon carbon bonds, that means the C2 C1 and C3 C4 are anti to each other, because that will be the stable form. Okay. And then you have 2 groups, the other 2 groups, okay. Other 2 groups which will be if you better first you convert it into directly into the kind of wedge formula. So, if you directly convert it into the wedge formula, what happens? It will look like this. This is the C1 and this is the C4. I am actually turning it this side little bit. So, now this X will be beta, will be towards me, and we talk about the back carbon C2. So, this X will be towards me, and the A. So, we are not talking about hydrogen here, we are talking about this is 1, that is 2. So, let us complete the 1. 1 has this X. So, as I turn it from this side, so X comes in front and B, X is attached to A. So, A goes to the back side, and the same thing happens here also, X in the front, and now it is instead of B you have A. So, this is the 3 carbon. So, that is the wedge formula of this, the wedge formula of this. Now, if you want to make it in a zigzag fashion, that means your C4 remains here, okay, on this side. So, you turn the C1 to the top to make it zigzag, and if you do that, C1 goes to the top, and here everything remains the same. So, X is beta, and your this is the alpha B, but here as you put a 180 degree rotation. So, X will become alpha and A will become beta, because it is a 180 degree operation. So, C1 goes to that side, X will become alpha, A becomes beta. Okay. So, this will be the situation. Now, this is the more preferred form of this molecule, because this is more stable. Now, you are not eclipsing X, you are not eclipsing B or A, you are not eclipsing most important the C1 and C4. So, another nomenclature system which says that forget about the Fischer projection, because it is in the eclipsed form. So, you better write the molecule in the zigzag fashion, the carbon chain in the zigzag fashion, and then you look at the atoms which are similar, which are the heteroatoms, that is X and X. If these two X's are on the same side, in this case it is not, this is beta, this is alpha. If they are on the same side, that is called erythro, like this, and if they are on the opposite side, that is called trio. Okay. So, based on that, write that in the zigzag, this is the carbon chain, the C chain in the zigzag, and then you look at the alpha beta nature of the heteroatoms, of similar heteroatoms. If both are alpha or both are beta, if both are alpha or both beta, then that will be called erythro, or if both are, one is alpha, one is beta, or vice versa, then that is called trio. Okay. Now, you see this will be according to this definition, this X is beta and this X is alpha. So, this will be according to this definition, this should be trio. Okay. Now, you see we started with the erythro form in the Fischer projection. So, if you follow the Fischer projection formula rule, then this molecule, the molecule which is erythro, that becomes trio in the zigzag rule, which was by the way proposed by a scientist whose name was Hitchcock. Hitchcock, he proposed this system, this trio erythro nomenclature, and based on the zigzag conformation. That means the actual, that is the conformation which the molecule mostly resides. However, that creates a lot of problem, because what is erythro in the Fischer projection, that becomes trio in the zigzag conformation, and vice versa. What will be, you can practice what is trio in the Fischer projection, that becomes erythro in the zigzag conformation. So, seeing all these confusions, there was another scientist who is at MIT USA, his name was Masamune. So, Masamune said that let us forget about trio erythro system, let us have a unified name which does not complicate the scenario further. So, do not call this alpha alpha beta beta erythro, he says that better call this as syn, and when it is alpha beta or beta alpha, you call it as anti. Okay. So, according to Masamune, that you still follow what Hitchcock said, that write it in the zigzag form, and now if you see that the similar heteroatoms have beta alpha configuration or alpha beta configuration, then you call that as anti. Okay. And if both are beta, then you call that as syn, or both are alpha, you call that as syn. So, that is the present day nomenclature for the relative configuration in case of molecules with multi-stereogenic center. You can actually, this was extended later for even compounds which are having more than two asymmetric centers. Suppose you have a molecule like this, you write the carbon chain in the zigzag fashion and see what is the alpha beta status of these X's. Okay. Suppose this is the number 1 carbon 2, 3, 4, 5, 6. So, this molecule will be called 2,3 syn, and then 3,4 syn, and also 3,4 and 4,5 syn. So, to describe this molecule you can say that this is 2 3 this is, or just say syn syn syn. Okay. That will of course take care, but it is better to mention the carbons that you are considering. Okay. If you change the suppose the middle carbon I change now, this I will make alpha. So, then what will happen? C 2 C 3 anti, and then C 3 C 4 anti, and C 4 C 5 syn. Okay. So, that is the modern day nomenclature. So, thioerythro is a very dangerous thing now to consider, because that as I said, that becomes exactly opposite. What is trio in this Fischer projection formula becomes erythro in the zigzag formula. Okay. So, now our modern day practice is to use the syn and anti relative conformation nomenclature for this type of molecules. Okay. Yesterday I was telling about like and unlike, and like and unlike I was a little confused at that time, that what is the, how do you say like, abbreviate like and unlike. What was, again I repeat, what was like and unlike? That if you have two centers, you determine the configuration at each center. Suppose this is R and this is R, so that is a like system, or suppose this is S and this is S, that is also a like system. And for unlike system, this is R, this is S, or this is S and this is R. Okay. This was proposed by Seebeck at the University of that is ETH, a famous university in Switzerland. He proposed this. So, this is your like and this is your unlike. But as I said, you want to abbreviate this, then I looked at the books. I thought that maybe this is LK, but then I found in Noshipuri's book that this is written as L and this is written as U. Okay. So, that is the abbreviated. So, just to dispel the confusion which we landed in last time, that what is the universal practice of writing this like and unlike conformation. Remember, this is applicable for all systems, there is no confusion at all. Only problem is, by looking at the molecule you cannot see the thioerythro, you can, by looking at the molecule you can immediately tell whether it is syn or anti immediately. But for assigning relative configuration for this molecule, you cannot really immediately say that whether it is like or unlike. Why? Because you have to do the configurational assignment R and S, then you can tell whether it is like or unlike. So, it is lot of work. So, that is why Seebeck systems was criticized, that like unlike, although it solves so much problem, that was there earlier thioerythro, but it has the criticism that you have to do this R and S in order to assign the relative configuration. So, that is a kind of little extra work. In this case, the advantage is, by seeing it you can immediately tell that what is the relative configuration, relative configuration in the molecule. Okay. So far we have discussed the last 2-3 lectures. We have discussed first the chiral environment, how to assign nomenclature for the chiral environment around a stereogenic center. Then we went how to assign the configurational nomenclature for molecules without any stereogenic center, which are actually chiral. Okay. And then also we tried to determine what is this relationship between the ligands. See, so far we concentrated on the carbon. So, there are two ways of looking at stereochemistry. Look at the carbon, which is the main cause for giving the chirality. That is one approach. The other is what happens to the groups. Do not forget the surrounding groups. Okay. Usually stereochemistry started concentrating all on this carbon, but then people started thinking of the groups attached to the, what is the relationship between the groups, not the relationship between the carbons, like in relative configuration. What is the relationship between the configuration of this carbon versus the other carbon? We are not looking, we are not seeing the interrelationship between the ligands. But yesterday we have shown that the interrelationship between the ligands are what are called topicity. The geometric relationship between the ligands in a chiral environment is what is called topicity, and we have identified different types of topicity. Homotopic, which are connected by C2 symmetry, and then heterotopic. Heterotopic has two types, one is enantiotopic, another is diastereotopic, and this heterotopic we are talking about stereoheterotopicity, not constitutional heterotopicity. Stereoheterotopicity we have discussed, and then we have identified their enantiotopic ligands and then diastereotopic ligands. Enantiotopic ligands were connected by either I or sigma or S, and diastereotopic ligands, because the molecule is chiral entirely, you started with a chiral center somewhere. So, the molecule does not have any of these symmetry elements, improper or proper. Okay. So, that is the relationship between the groups. There is a third now scenario where you have the chiral molecule, and then what happens to the space surrounding the chiral molecule? What is the relationship between the faces of a molecule? Suppose I have this double bond compound. Okay. Suppose this is an aldehyde, this is suppose a hydrogen, this is another group, and this is an oxygen. Now, if I place it in the horizontally, then it actually is dividing this entire space into two. One is above this plane, this is a planar molecule, and the other is below the plane. So, there are faces, there are two faces, and these two faces may be same, may not be the same in stereochemical sense. How do you know that? So, if I add something now onto this carbon, because carbonyls are susceptible to nucleophilic attack. So, the nucleophile can come from the top or come from the bottom. The question is, will it lead to the same compound or not? So, that means, if they lead different compounds, that means two faces, these two space on the top and the bottom are different. Okay. Or if they lead to the same compound, that means these two faces are same, there is no difference. So, that is another one. So, we have done the relationship between the carbons, relationship between the ligands, that is the topicity, and now what we will discuss the relationship between between the spaces that the molecule is dividing, the three dimensional space that is being divided into two. Now, what happens? Suppose I take again back to this example, say hydrogen and methyl. Now, this is a planar molecule, this is in the plane of the board. Now, so this is dividing this space, three dimensional space into two halves basically. One is towards this side, another is the space we cannot see, because this is a room behind this board, that is the other space. Okay. Now, if you add, because these two groups are different, if you add a nucleophile from the top, so what you will get, the nucleophile will definitely take up a beta position, because it is coming from this side, it is above the plane of the board, and what goes, so this will be the as it comes from this side, so the weight will go down. So, weight that this double bond breaks, the nucleophile comes from the top, the double bond breaks and becomes a wedge. So, that and these two remain the same, the hydrogen and the methyl. So, this is one compound that you will get if it comes from the top face, the face on this side. If it comes from the bottom face, you get exactly the opposite compound. The enantiomer of this. Okay. So, these are enantiomers. So, now because addition leads to a set of enantiomers, addition from one side leads to one enantiomer, addition from the other side leads to the other enantiomer. So, these faces are, first of all, these faces are now no longer similar, and they now have a, you have to assign a name to this, because like we have to, we will also go for ligands also, just like we have assigned absolute configuration of this carbon, which are having attached to 4 different groups. Similarly, this space has to be given a name. Suppose I have some restriction that this is a wall, the reagent cannot come from the bottom side, the nucleophile has to come from this side, then I will only get this compound and not that compound. Okay. So, there must be a descriptor for the faces that we have. We cannot just say top face and bottom face, because the same compound can be obtained if I write it in a different way, the methyl at the top and the hydrogen at the bottom. Now, to get to this compound, the nucleophile has to come from the back side, because it is written just in a reverse fashion. So, the back side now becomes identical to the front side if you write it in this fashion. Okay. So, we need to describe the topicity of the face, the relationship between the faces. Okay. So, again there is a nomenclature system, very simple. This is a, remember another point, that if this is no longer a hydrogen, suppose this is a methyl, then addition of the nucleophile does not create any asymmetric center. Okay. So, then the question of the two faces are same, because it does not matter whether nucleophile comes from top or bottom, it leads to the same molecule. So, there is no question of topicity of the face. Okay. It is there once these two groups are different, that is the thing. Now, how to assign the descriptor for the two faces? This is done by again giving priority. Now, we have 3 ligands to this carbon. So, giving the priority according to the atomic number. So, this is number 1, this is number 2 and this is number 3. So, 1, 2 and 3. So, you see what is the direction from going 1 to 2 to 3. So, this is now clockwise. So, this face, that means when I see from this face, this looks clockwise. So, this face will be called a ray face. Okay. There are some books write it capital and small, both are okay, but I prefer the small one, the ray face. Remember, this is actually, again it should be written in italics, because these are again coming from Latin words. Okay. So, this is now becomes a red the ray face, and if I say what is the face which is behind this board, if you look from that side, the direction, like yesterday I told you that if a fan is rotating in a clockwise direction, if I see from bottom side it is clockwise, then from the other side it will be anti-clockwise. So, because I cannot go into the back side and see the molecule, because there is a wall now which is preventing me to do that. So, I will, if I look from the back side, the same direction will now be anti-clockwise. That means, the other face is what is called a side face. Okay. So, now the faces are also have these descriptors, the ray face and the side face. So, if there is a reaction and if I tell that the nucleophile is adding from the ray face, so you can immediately figure out that what is the ray face, and you can draw the geometry of the product. Interestingly, as I said that when you write these two systems, this methyl and hydrogen, if you write in the opposite way, so now what will happen? This is 1, this is 2, this is 3. Now, this side becomes the side face and the back side becomes the ray face. And I told you that if you write this way, if the nucleophile comes from here, it gives this product, it is the same product from this conformation, from this form, if the nucleophile comes from the back. But that means you might be confused that back and front. So, as I said, back and front does not have any meaning. You have to assign the ray and psi descriptors for the faces. So, if I write it in this fashion, this side is the ray face, back side is the psi phase. If I write this molecule in this fashion, now the back side will be the ray phase and the front side will be the psi phase. Okay. So, from now on the phases should not be front or back. If you want to give stereochemical descriptors, you have to say ray and psi. Okay. That will be very important when we discuss reactions, the reactions involving stereochemistry, chemical assignment, where you generate a new chiral center. Now, by the way, this carbon is called a prochiral center, because this is not a chiral center, but as soon as you do one transformation, you convert it into a chiral center. So, if by one transformation you can convert a carbon into a chiral center, that carbon will be called a prochiral center. Now, this is not only restricted to a carbonyl, it is restricted, it is also applied to systems like this. Yesterday we have seen these molecules, these two hydrogens are enantiotropic. Okay. So, here also this carbon is a prochiral center. This is not chiral, because all the 4 groups are not same, these two hydrogens are same. But if you replace, if you by one transformation you can replace it by X, you immediately convert into a chiral center. So, this is called, so that will be a prochiral center. Okay. So, by one transformation if you can convert a center into chiral center, then the center will be called a prochiral center. And so, then what will be the center where there are 2 transformations needed to make it chiral? Like if you have this compound CH3CH3, and if I ask you what is this carbon, see, by one transformation you cannot get a chiral center, you have to make 2 transformations. This hydrogen has to be replaced by X and this hydrogen has to be replaced by Y, then only you can get a chiral center. So, there are 2 transformations needed. So, this will be, so when you have these all hydrogens, this is called prochiral center. There are 2 pros, because you need 2 transformations to convert it into the chiral center. Okay. So, we have seen that there will be that phases, how to give stereochemical descriptors to the phases, which are basically attached to the 2 sides of a prochiral center, and the ray and the psi phase have been introduced. In the, you can also assign, because it is a, when there are 2 groups C2H5 and CH3, when this carbon is, okay, when this carbon is a prochiral center, these 2 hydrogens are enantiotropic, and you can again assign stereochemical descriptor to these hydrogens. Okay. That we will do in the next lecture. Thank you.